Hey, hi, good morning, everyone. Good morning, friends. Welcome back to our series on convolutional neural networks. So, yesterday we have successfully, started this particular playlist where we are going to discuss convolutional neural networks. So, friends, if you are joining for the first time, do subscribing. Consider subscribing because we are going to do n number of programs in the upcoming future. So, we'll quickly recap what we have covered in the previous session, then we'll start. Right. So, in the yesterday's session, introduction to CNN, convolutional neural networks, we understood the basic topics like image. What exactly is image? Image is nothing but a collection of pixels. Okay, if you have an image in this way, I'm going to represent the same image in the form of a grid, a table, in which I'm going to represent the image with numbers, and these numbers are talking about color information. Okay, they are nothing but pixels. Okay, so in simple, image is a collection of small dots. So these are the dots where we call it as pixels. Okay, each and every pixel that we have with the value, they hold the information of color. Okay, whatever the colors that we have within the image, the value of this pixel is going to represent the color information, right? Then we understood the different types of images that we have. We have grayscale image, a black and white image, and we also have you know colored image. So two types of images we have discussed. One is grayscale image, also called as black and white. Then the other one is colored image, which is RGB. Okay, there are three channels: red, green, and color, blue. Yes. So grayscale image, you'll have only the values of the pixels ranging between 0 to 255, where 0 represents black and 255 represents white. Yes. All right. So the values between this range 0 to 255, they talk about uh, different shades of green. Okay, if the values are ranging between this particular range 0 to 255, they are nothing but they represent different shades of gray color. I hope it's making sense. Then we also discussed color images, okay, which is nothing but RGB. We have red, green, and blue as the channels. And for an colored image, we represent the values in a 3D array. Okay, we represent the values in a 3D array. Okay, so this 3D array, where it has three values, one represents height, the other one represents width, and the third one represents channel. Okay, so this particular colored image will have channel as 3. Height and width will keep on changing. Depending on the image, it changes. Making sense? Yes. So we discussed the value for red color. It will be 255 comma 0 comma 0. Then for green it will be 0 comma 255 comma 0. For blue it will be 0 comma 0 comma 255. These are the values for the colored images, RGB channel. Right. Any questions so far? No questions, right? Because these are the basic topics that we have covered. We understood CNNs, convolutional neural networks, are generally used for image data. Okay, so images similar to videos, yes, we have images and videos as the same, because video is nothing but a collection of frames, a series of frames where frames are nothing but images, right? Yes. So in today's session, let us go and understand the architecture of convolutional neural network. So yesterday I was questioning regarding what is the general meaning of convolution. Because if you are aware of what the meaning for convolutional word, then this particular neural network concept you can easily memorize. Because the meaning for convolution, the meaning for convolution is referring to a mathematical operation. Okay, so when you have two functions, when you have two layers, and if you are going to overlap one over the other, then we call it as convolution operation. So the same operation is what we are going to do in convolution neural network. Okay, so what exactly is this convolution operation? We'll understand, friends. Making sense? So let me start the working principle of convolution neural network. Yes, so CNNs are explicitly designed for image data. Okay, it might be images, videos. Yes, videos are again the same. Then why traditional ANNs, neural networks, cannot be used for image data? What is exactly stopping this ANNs to use for image data is the first and the foremost challenge that we observe is dimensionality. Because when you have an image of size 100 by 100 and this is a colored image, assume. Okay, so the size will be represented in this way: height, width, and channels 3. So when you multiply all of these, you'll get 30,000 as a value. Yes, obviously the output is 30,000. So that means in the input layer itself, you are going to have 30,000 features. Oh my God. So this is again just for 100 by 100 colored image, which has 3 channels. Apart from it, assume if there is an image which is of high resolution, 1000 by 1000, or again it's a colored image, then probably the size will be keep on increasing. Yes, again you multiply by 3. So 1000 multiplied by 1000 is 10 lakhs. Again, so this will be multiplying with 3. Obviously, you are going to get 30 lakhs. So that means here 30 lakh inputs is what you are going to get. So these many inputs is what you'll have initially. We did not start the operation, friends. So at the initial layer itself, you'll have these many number of inputs, and which is going to cause high computational burden on the machine. Yes, so this is the first and the foremost challenge. Because of the high dimensionality, we cannot go and use the traditional ANNs. Okay, so traditional ANNs, this is this is how traditional ANN looks. Input layer followed by hidden layer, then coming with output layer. So in the input layer itself, you will have 30 lakh features. So that means each and every neuron which is going to take one feature, you should have 30 lakh neurons. So, not accepted. In the input layer, if you have 30 lakh neurons, what about hidden layer neurons? More than it. So this is going to cause computational efficiency. There will be a lot of load on your machine, and your machine should be very expensive to train such kind of data. Yes. So this is actually stopping to use traditional ANNs for image data. Okay. If you have videos, image as your data, you cannot use traditional ANNs to train the model? No. Then came CNN into the picture. Okay, so the architecture of the CNN is similar to ANN, but there is a difference between ANN and CNN. Okay, so we'll have convolutional layers, we'll have pooling layers, then we'll have fully connected layers. What are these? What are the advantages of CNN is no, the parameters that we are going to come up with, they'll be reduced. We'll not have these many features initially. Okay, the number of parameters get reduced, and we can also extract the features. Whatever the features that we have in this image, we have a bird, right? So we can extract the features automatically. How? We'll understand, no worries, right? So let us understand the operation of or the working of convolutional neural network. You take an image. Any image will be represented in the form of an array. Yes. Okay. So when I'm taking an image which has a digit 8, I'm trying to represent this 8 in the form of pixels. Right? See. So the same image I'm going to represent in the form of pixels since it is a black and white image. So the values will be from 0 to 255 only. So I have normalized the values and I'll get the values only between 0 to 1. So when you normalize the values to by 255, so you get the values between 0 to 1, right? So this is how you represent the image in pixels. Now, let me talk about the components of CNN. CNN in convolutional neural network, you will initially have the input, the image or the video, whatever you have, you'll take the input, the image as an input, and then you'll have convolution layer. Okay, so what exactly happens in convolution layer we'll discuss. Followed by each and every convolution layer, we have a pooling layer. Is it mandatory? May or may not, friends. But a convolution layer followed by pooling layer will reduce the dimension. Okay, so what is this pooling layer? What is convolutional layer? We'll understand. Okay, then after having pooling layer, we'll have fully connected layer and finally output. So this is the basic architecture of CNN. This is how we are going to have a CNN architecture. All right. Let me start with the input layer. So in the input layer, we are going to pass the raw data, the image, right? So this image will be converted in the form of pixels, depending on whether it's a grayscaled or a colored image, a black and white or a colored image. We are going to represent the channels also. So the dimension of the image will be represented in this way: height cross, width cross channels. So once if you have an image, that image will be fed to the convolution layer. What happens in convolution layer? In convolution layer, the actual journey happens. The process of convolution happens in convolution layer. What is this convolution? Okay, what is the process of convolution? Hold on, we'll discuss. Convolution is nothing but, when you have two objects, okay, when you have two functions, you're going to multiply one with the other, right? So that is nothing but convolution. It's a mathematical operation. Anyhow, I'll explain it. So in convolution layer, we'll apply something like we have filters, also called as kernels. We apply filters to extract the features. So within an image, you will have some important features that has to be extracted. So these features will be extracted using, kernels, also called as, filters. So these filters kernels are responsible to identify the patterns, identify the edges, the textures present inside an image. Okay, so once after applying a filter, a kernel on the image, we'll also perform activation function. Okay, in general, ReLU is used. Okay, so we introduce non-linearity to the model by including a activation function. Yes, this helps us to include some non-linearity. And moreover, the non-negative values that you'll have after performing convolution operation will be reduced by ReLU. Yes, because ReLU works on a function and the function is given as max of 0 comma x. Okay, so if the x value is less than 0, output will be 0. If x value is greater than 0, obviously the x value will be written as it is. Right? So introduce non-linearity, we use ReLU as an activation function in convolution layer. Then we'll also have pooling layer followed by convolution layer. So this particular pooling layer helps us to reduce whatever the output that you get from here. Okay, so that dimension will be reduced by pooling layer. Okay, we use max pooling, average pooling, min pooling, global pooling. There are many types of pooling. We'll understand what is pooling and what are the different types. But the purpose of using a pooling layer is, it reduces the dimensions of the output that you get from convolution layer. Okay, whereas the important information, whatever you have, will be kept as it is. And next to pooling layer, we'll have fully connected layer where this output of pooling layer will be converted as a flattened layer. Okay, all the pixels will be converted as a flattened layer as a single dimension array, and that will be used as an input for fully connected layer. So this is representing a dense layer of friends. I hope you remember. So when a neuron, whenever you take a layer of neurons, so within that layer, if all the neurons are connected to all the rest of the neurons in the previous layer, then it becomes a fully connected layer, a dense layer, right? So within the fully connected layer, we'll also have the output layer, and which helps us to classify the image or do the respective task for detection, classification, segmentation. Depending on the task, we use the activation function as well. So this is the overview of CNN architecture, but majority of us will not be clear on whatever we have discussed so far, but I'll walk you through convolution operation that happens in convolution layer, and we'll also understand how ReLU is used as an activation function in convolution layer, followed by pooling layer. What are the types of pooling layers we have under pooling layer? Then how the values of the output of pooling layer is converted as a flattened layer and how it is used as an input for fully connected layer, we'll understand. The journey is simple, friends. This is how a CNN works. Can we have multiple? So if you see here, convolution layer plus pooling layer is nothing but a feature extraction layer. So in this particular layers together, we are going to extract the features that we have inside an image. Yes. So what is the purpose of using CNN? To extract the features. Whatever the features that I have inside an image, they has to be extracted. So that is done using both convolution layer and pooling layer. I hope it's making sense. Now let us go and understand the concept of one by one. Okay, I'll start with input layer, then now we'll go on further, friends. Right. So initially, we'll have input layer in which the raw data will be passed. Okay, so depending on the type of image, we are going to fix the channels. For a grayscale image, channel is 1, obviously. But for colored images, RGB images, the channels will be 3, red, green, and blue. Right? So if I have an image which is grayscale, which is black and white, so the third dimension, height multiplied by width multiplied by channels. So this becomes 1 for grayscale image. But for RGB images, the channels, number of channels will be 3. So even though if you don't represent channel for grayscale image, that's okay. Because anyhow, it's 1, right? 1 multiplied with any number, obviously, it returns the same number. So that is the reason we ignore the number of channels for a grayscale image, a black and white image. So what happens in input layer? In input layer, the data or the image that you have will be represented as pixels in the form of pixels, where the image will be represented in a matrix or an array. If it is a matrix, though obviously you'll have only rows and columns. So if you are working on colored images where you have multiple channels, so obviously it becomes a array, three-dimensional array. You'll have three dimensions, height, width, and channels. So assume I have, you know, a grayscale image. Okay, so this grayscale image is I'm going to take a grayscale image. So obviously I'll have a matrix. So this is my matrix. Okay, so this is my input, and this input I'll be passing to the next layer. It is convolution layer. So this is where the main operation happens. The convolution operation happens in convolution layer. Okay, so what exactly is convolution operation? We'll understand. Yep. Now focus. What's happening? First of all, I have an input. See, anyways, it's not stopping. That's fine. So initially, I have an input which is represented in the form of pixels. So this blue matrix that you see is my image. What is the size of my image? It is 5 cross 5. Am I right? Yes. So that means I have 5 rows and 5 columns. So all of these values are normalized, friends. So that is the reason you are not seeing a big number of value. All right. So 0 to 1, that's it. Now, under convolution layer, you will take a filter. So this, I'm going to take a filter. Okay. So these filters are called as kernels. We use filters, kernels, to extract the important features of an image. So it might be an edge. So for example, if within our input image, okay. So anyhow, I cannot draw a cat, but if there is a cat, okay, if there is a cat, and if I want to extract the features of a cat, so I should detect the edges of the cat. Where exactly cat is present inside the image, I have to detect. Yes, I have to detect the texture of the cat. Yes. So these edges and textures can be captured using filters. How? So the filter or the kernel will undergo convolution operation. So it is represented with star. Asterisk mark that you see here is nothing but convolution operation. To perform convolution operation, where the values within the filter, okay, you'll again have the values. So the values here are 1, 0, 1, 1, 0, 1, 0, 1, 0. Okay, so you'll take the values, you'll fix the values inside the filter, and this filter will undergo convolution operation. So that means, this particular matrix will be multiplied with a subset of values. So it just slides on the input image. I hope it's making sense, right? See, I'll go back. You observe carefully, it starts from here. So initially, the first 3 rows and first 3 columns will be occupied. Okay, so where the particular filter gets performed the convolution operation, and it gives the values. Okay, then it moves to the next row. So in this way, it just overflows on our input image. Okay, it slides on our input image, and we are going to complete our convolution operation to get the output. So if you see here, obviously our input image is written over here, and by using a filter, I'm going to get this is my filter. So if I use this filter on the input image, I'm going to get the output matrix. What exactly is happening is, so if you see 0 multiplied with 9, it's 0. Then 2 multiplied with 4, 8. 1 multiplied with 1, 1. In this way, each and every value, as part of this operation, each and every value gets multiplied and they get summed up to get the final value. This is nothing but convolution operation, right? So what's happening is, when we perform convolution operation, let me execute it. See, observe carefully in this region. So whenever it's sliding, it's giving the output. So initially I took a filter, and that filter is being slide on my input image to get the output. So this filter or kernel helps us to extract the edges, the patterns, the textures from the input image. So what is the formula? How can we calculate the output image size? We have a formula, friends. For that, we have a formula. Sorry. So what is the size of the filter? It's 3 by 3. What is the size of your input image? It's 5 by 5. So output image size will be, your input image I'm taking as, N, and the size of the filter I'm taking as F, and this is represented as N minus F plus 1. So what happens? What is the size of your input image? 5. What is the size of your filter? 3. So 5 minus 3 will be 2. 2 plus 1 will be 3. So I should get a 3 by 3 image as output. Hope it's making sense. This is one of the important formula in CNN, convolution neural network operation. Okay, so under convolution, it is just in simple terms, you can remember dot product, right? So the values of the filter will be slided on the input layer, on the input image. It multiplies with the values to get the output. So if you take only one particular, if you want to concentrate on one particular value in the output, so we have a detailed explanation. So 9 will be multiplied with 0, 4 will be multiplied with 2, 1 will be multiplied with 1, and so on to get the value as 16. I hope it's making sense. So this is how convolution operation occurs. But the majority of us, will be clear on what is convolution operation. By now, yes, convolution operation is nothing but sliding the filter on the input image to get the output. So this particular filters are the kernels help us to extract the features, the edges, the texture from the input image. So from the input image, in order to get the important features, okay, in order to get the important edges of the image, yes, we use filters or kernels. I hope it's making sense. But the question comes, what should be the size of a kernel? Okay, what should be the size of a kernel? Kernel is generally, they are a small matrices. Okay, it might be a 3 by 3 shaped kernel, or a 5 by 5 shaped kernel, or 7 by 7, so on. Okay, so these help us to extract the information from the input data, from the information from the input image. So They also help us to detect the specific patterns like edges, textures, or shapes. So we'll have complex objects, right, within an image. In order to get the shape, the edges, we use different kernels. Okay, not every time the same values will be used, friends. I hope it's making sense. So the values, if you change the values inside the filter, the kernel, so immediately your output will be changing, and this particular output will have a different edges captured. And when you're changing the values of the filter, obviously it is going to capture some other edges or some other shapes from the input image. Okay, so by this we can understand that we use number of filters. We use not a single filter as part of convolution layer. We can use n number of filters or n number of kernels to get the hidden patterns, to get the important patterns, the important edges, because not one particular filter, not one particular kernel is going to get all the edges from our input image. I hope it's making sense. So here we had an example. See, if we are going to use 32 filters, the layer will output 32 feature maps. So that means if I'm using one filter, how many outputs I'm going to get? One? Yes. One output is what I'm going to get. So in the same way, if I use 32 filters, so it will be like, so 3 by 3 by 32. Where this 32 is representing the number of filters that you are going to use. So whenever you use 32 filters, the output feature, I mean, whatever the output that you're going to get as part of convolution operation will also have 32 images, 32 outputs, each of size 3 by 3. Making sense? Yes. So the question again, what should be the size of kernel? Okay, so in general, we always go and use smaller kernels. Okay, so when you use smaller kernels, what happens is they are used to capture fine-grained features like edges. So in order to capture the edge, so the outlook of a cat or an image, within an image, I have an object. So of an object, if you are going to capture only the edges, then go and use smaller kernels with smaller size. If you use larger kernels, 7 by 7, 5 by 5 and all, they help us to capture the border patterns. But this is, yes, obviously computationally expensive. Why? The number of values within your kernel, within your filter is being extended. 7 by 7 means how many values you'll have? 49 values, friends. So when you have 49 values, obviously it will be computationally burdened, right? So that makes the difference between the values. If you take a smaller kernel, it helps us to capture, the small patterns, the fine-grained patterns like edges of an object inside an image, input image. And if you're going to take a kernel with high dimension, so this is going to capture the border patterns. Okay, and this is, yes, obviously computationally expensive. Okay, so depending on the features that you want to detect, your kernel size should decided. Yes, depending on it, we are going to decide the features. So I hope everyone is clear on convolution operation. So now let me start the next task. Okay, so if you are clear on convolution, you can just proceed to the next topic, that is stride. So the question comes, Akhil, why are you, when you are performing convolution operation, why are you going and just sliding the kernel only one step? Why not 2 steps or 3 steps? So this is called as stride. So how many of you have gone through my Python sessions? So in the previous playlist, I have also covered Python. Why am I asking you the question is, in Python, we discussed a function called range. Hope you remember. Range. We have str category data type inside which we have range. So we are not to create a range object, we define start, step, and step size. Start, stop, and step size. This step size is also called as stride. This is called as stride. So what exactly is stride? Stride is representing the step size. So your filter is moving across your input, right? So if this is your input, okay. So your filter is it's moving across your input. This is nothing but convolution operation. But the step size, whatever the filter is going to take, okay, it's sliding across your input image is called as stride. Okay, so what does stride means? I hope it's clear. So stride is representing the step size of the filter which is moving across an input image. So stride of 1 represents, that means you leave one column at a time and go to the next level. Okay. Then after completing this convolution operation, again go to the next level by leaving one column. So in this way, you'll complete, this entire rows, all the rows at a time. Then you'll come down by leaving one row at a time. So this is stride 1. Okay. What is stride 2? Once if you had, okay, what is the filter that I'm taking here? So initially I had a 7 by 7 image, input image, where I'm taking my filter size as, 3 by 3. So if you see here, initially this particular 3 rows, it performs the convolution operation and we are going to get a value. We are going to get a value. If I go with stride 2, I have to leave 2 columns. It's not one column. Stride 1 represents, skipping one column at a time. That's nothing but skipping 1 pixel at a time. But stride 2 represents, we are going to skip the alternative pixels. So what exactly happens is, so instead of skipping one column, I should skip these 2 columns. I have to start from here. So this is how I'm going to get. Again, I have to skip 2 columns. So this is how I'm going to get. So in this way, you can also decide your stride. What is the purpose of using stride is, deciding stride is, it is going to reduce the output dimension. A 7 by 7 image, input image, if I'm going and using stride 2, what it is going to happen? See, even here, I'll reduce this 2 and I'll get output here, then here, then here. Okay, again 2 rows will be left. So a 7 by 7 matrix is going to convert it as 3 by 3 as output. Think. So this is actually helping us to reduce the output size. Stride helps us to reduce the output size. So larger strides is going to result us in smaller input. That's what we have observed. When I use stride as 1, 7 by 7 became 5 by 5. If I use stride 2, 7 by 7 became 3 by 3. So when I'm increasing the stride, I can observe that my output size get decreased. So this is size, stride, and this is output, size of the output. Okay, and this is also going to faster the computation, but it may lose the information, friends. Whatever the information that is present in the rows, okay, so it is going to skip the rows, right? So there it may lose the information. So stride helps us for faster computation, but we have a disadvantage. It may undergo, loss of information. Yes, it may lose some information. Making sense. So stride, we are clear. Now let us also discuss what is padding. We also have padding because padding is again one of the important concepts that we have in CNNs. So what is padding? Padding is nothing but it refers to adding extra pixels. So if this is your input size, okay, which is of 3 by 3, I have an input image of size 3 by 3. So when I take a 3 by 3 image, okay, and what if I have, uh, okay, if I have my object somewhere here in my image, in this particular, cell, when I take a 2 by 2 filter on the same image, input image of 3 by 3, what happens? So initially these two layers on these two, rows and columns, the convolution operation occurs and I'll get one value, one output. Then it skips the first column and it goes to the next row. Okay. So in this way, the convolution operation is just happening only for once for this particular cell, right? But if you take this cell, once here, then second time it occurs here, third time, fourth time. So that means for this, you know, uh, for this cell, the convolution operation, the value in this cell is being included in the convolution operation for 4 times. But the value in this particular cell is being used for only once. So what is the purpose of padding is if you have any of the important information, okay, the important information within an image at the edges, corners in these areas, okay, so they don't get more attention because they being the information being at the corner, they don't get more attention. So we use a concept called padding, which helps us to add extra pixels. We add extra pixels around the input image so that even though if you have an important information at the edges or the corners, okay, even though if you have the information here, or it might be here or here, the information can be identified. The important features can be discovered. So that is the help of padding. Padding helps us to add some extra pixels around our input image. So this is input image. What I'm doing, I'm just added 2 rows and 2 columns. So my input image, which is 3 by 3, now it became 5 by 5. So this padding helps us to give attention to, the information which we have at the corners. Okay, if there are edges, if the object is present at the corner of the image, then obviously I should go and use padding, right? So this is one of the important topic, padding. And there are 2 types of padding, friends, valid padding and same padding. Okay, so what is this valid padding? Valid padding is nothing but no padding is applied. The output size is smaller than the input size. Okay, so whatever the output size that you're going to get will be smaller. So that means there is no padding done. Same padding is nothing but padding is added so that the output size is same as the input size. So it will be same as the input size. So when you do convolution operation on the padded image, you're going to get the output. Yes. So that output size will be same as the padded image size. So that is nothing but same padding. Now, I hope we are clear on convolution operation and stride and padding as well. Okay. So once after completing the convolution operation, we'll get an output. Yes. So within that, matrix or an array, I have some negative values. Can we have negative values as part of the output from convolution layer? Yes. How come, Akhil? If the kernel values within the kernel, within the filter, if you have negative values inside your kernel, then obviously, you may get negative values as part of your output of convolution operation. So I use an activation function, especially ReLU, to introduce nonlinearity. Okay, when I use ReLU activation function, so this is the formula that is used by ReLU, rectified linear unit, max of 0, comma x. So this is going to set all the negative values present in the output to 0. How come? Simple. Max of 0, comma minus 7. What is the x value here? Minus 7. So between 0 and minus 7, what is the maximum value? 0. So ReLU helps us to get all the negative values set to 0, and it will have only positive values. It will have only positive values. Okay. If you take, if you also have, you can also have other, activation functions like leaky ReLU, okay, tan h, then ELU. Okay, these are generally used. Yes, right. So that is how we go and use activation function inside once after completing convolution operation. Okay, then we have pooling layer. So probably in the next session, we'll discuss what is pooling layer. Okay, what is the purpose of using pooling layer on the output of convolution operation layer? Okay, once after you get a convolution output from the convolution layer, that will be passed to pooling layer. Why? What is the purpose of using pooling layer? We'll understand. Then this output from the pooling layer will be convert to a flattened layer. Why? What is the purpose of converting into a flattened layer? That output again is sent to fully connected layer. Okay, so we'll understand all these topics in the coming session. And yes, later on we can also implement CNN on a use case sprints. I hope it's making sense. So I'll stop it here. If you have any questions, yes, feel free to ask. Till convolution layer and the activation function. So if no questions, feedback link will be shared. Share your valuable feedback, suggestions. We'll try to enhance our sessions in upcoming programs. And moreover, uh, when you're going through these sessions, and if you got any kind of questions, post the questions in the comment section. We'll respond immediately. Right. So that's all for the day. Again, we'll meet in the next session. Until then, take care. Have a great day. Signing off.